this video, I'll show you how I made this flag detection AI model you're seeing here, which got the highest AI score for ICMTC competition, helping the team get the second position. Without further ado, let's go. This is the data the team provided to us, and we need to create a model that can detect country flags in a desert. And it's actually looking quite good. That's capturing wide range of the desert. The issue is that it's taken from a single time, so we don't have much of a color shift or time shift in the desert itself. And another big issue we have is that this doesn't actually contain any flag. It only got this single flag here of Egypt. And of course, a single flag to train an entire model to detect all flags is not possible at all. So we most likely won't use this flag here. Instead, we will extract a bunch of frames or images of the desert out of this video, and then artificially add flags to those extracted images and define the boundary box, and this will be our dataset. Let's start with the image extraction. So we start off by doing some library imports, and we define some important buses like the video bus itself and the output bus for the images frames, both for training and for validation. Then we define some important parameters like the FPS of the video, start and end frame, just to cut out the useless parts of the video, and our sampling rate is 3 frames per second, just to maximize our variety. Frame index to keep track of where we are currently in the video, and 2 variables just to track how many training images we have and how many validation images we have, and the probability that the image will belong to the validation set. Now the main loop itself, which is just a simple loop that ensures we don't exceed our end frame. We set our capture position at this frame index, read the frame itself. Finally, we update our frame index in a way that allows us to capture the amount of frames we want per second. Now we decide if our frame should belong to the validation set or the training set, according to our validation probability variable, which is set to 20%, and set the bus to save the image accordingly with a unique name. Finally, we resize the frame to a lower resolution and save it, and then print how many training and validation images we got. So for the training pipeline, we'll start by doing some imports and bus definitions for the desert background images and other files. Now for our synthetic dataset, this is the entire code for it, which may look a bit complicated for now, but don't worry, by the end of the video you'll fully understand how it works. So let's simplify it to its bare minimum. We just have a simple class that extends PyTorch dataset. The constructor takes a directory for the background directory, the desert images, and a directory for the flag buses, number of samples, or like how many samples do you want to generate for this dataset, an image size to resize our images to, which actually should be 640 by 640, and maximum number of flags we want to paste into our image. Any PyTorch dataset must require a $len method that returns how many number of samples or how many images we are gonna generate for this dataset. Regarding these labels of self.getLabels, this is just something required by YOLO. It just adds some metadata to the training object itself, like its class, keyboxes, segments, key points. So this is the expected format for a dataset to be valid for YOLO, so we must have it. Now let's create an instance of this dataset, and of course we need to have a directory for our flags. So let's add it here. So yeah, just the flags directory, and we are sorting the flags, forking every PNG image there and turning it into an array, splitting it for validation and training. And in case you're wondering, those are how the flags look like. Country flags of almost each country. I got them from here. Thank you, Cole. Your dataset is an insane W, honestly. Anyways, let's run. No errors here. Now, what happens if I try to access dataset at zeros element? Of course, an error because I don't have the getItem method. So let's create it. We are just gonna pick a random desert image, convert it to RGB, and permute its channels, because of course a normal image is height x width x channels, while PyTorch requires it to be of shape channels x height x width. So that's why we are permuting it this way. Now if I run this code, I get my dictionary back of my image. So let's actually try to plot it. And yeah, it's working. Let's just make it look nicer. Of course, we are now returning just a single image, but we aren't returning its label, its class, its boundary box, any of that. So let's just add some dummy placeholders for all of this. Placeholder for the class, boundary boxes, and the batch index. Again, YOLO just requires it in this specific format. Now let's paste a random flag on this image. Let's go here. Make a random choice from our flag buses and convert it to RGB. Then we resize it to 100 pixels by 100 pixels. Then pick the position we want to paste the flag into. And finally paste the flag. Now if we ran this code, you can see we got an error saying bad transparency mask. To fix this issue, we just need to introduce alpha channel to the flag image. And yeah, we can see our flag being pasted correctly. Now the issue we have so far is that this image thingy at its boundary boxes is still the dummy placeholder, which is not what we want. We want it to contain our boundary box for the flag we just added. So to do this, we just go here,
This is the format of a boundary box that YOLO expects. We just need to have the center X and center Y, and we're getting it by adding to the position basis of our flag in half of its width, and same for the Y axis, adding half of its height. And you can see we're dividing the X by its width and the Y by the height. This is to convert it to proportions from row pixels, which is required by YOLO. Finally, the width and height are just the flag width and flag height being converted to proportions as well. Now we just append this to our labels array. 0 is just the class of our object, and here it will always be 0 as for the flag. Then we're going to convert everything to tensors and finally use it here. Now if we run our code, nothing will change in the image itself, of course, but you can see we got some values for our boundary box, and we will also have some values for the class itself, which will always be 0. And by the way, I could, instead of adding this 0 here, I could simply turn this to tosh zeros and whatever the length of my labels are, and this will work perfectly fine. And then I won't need the zeros here, and I don't need this anymore. I can directly use the labels tensor, and you can see it will still work perfectly fine. But the reason I did this is to be more flexible. Like, what if I wanted to add multiple classes in the future? Like, hey, I want to detect both a flag and a car, for example. In this way, we will need to do a lot of refactoring, but in our original code, we can just, in the loop that's adding multiple stuff, we can directly change this class to whatever we want, and it will be automatically reflected here. Now, a good habit is to always visualize our work. So we added boundary boxes, and now we need to visualize them to ensure they are actually being added in the correct position. And yep, I can see my boundary boxes being added perfectly around the flag. Now, as of now, the flag position is exactly at pixel 50-50 each time. There is no sort of randomness, which will cause our model to just memorize returning this value all the time. So we just need to ensure some randomness here. So now our flag will be pasted in random position each time. And actually, the flag is way too big for our real life situation. So if we looked at the video, you can see that this is how large the flag is actually as compared to the desert. So this scale doesn't reflect what the model will see in real world. So we need to make the flag smaller. And actually, instead of it being a constant value, let's enforce some randomness. So we pick a random scale percentage. We multiply the width by the scale percentage, and same goes for height. And finally, we use it here. So flag width and flag height. Right, looking good. The final thing I want to do is to randomly rotate this flag. So let's pick a random angle to rotate the flag with between 0 and 360 degrees, and finally rotate it here. Now, a nice trick to speed up our model is that instead of the model being able to see a single flag per each image, we can add multiple flags, so the model can learn on multiple instances of a flag on a single image. So let's just add a simple loop here, looping over our max flags range, which is set to 5 by default, and just append everything here to this loop. Actually, we don't want to include this in the loop, so just still here. And if I run this code now, yep, working perfectly. Now, something funny that can happen is that it will be clear if I increased my maximum amount of flags to say 100, for example. If I zoomed closely into my image, you can see there is something quite funny happening here. There are some flags that overlapped, okay? And same thing happened here, 2 flags overlapped. Same here, almost overlapping, those 2 are overlapping. And there are lots of overlapping here. And is this a bad thing, really? Well, this depends on what your AI model will see in real world. If your AI model is expected to see many flags on the ground, and for example, it should like count how many flags are there, then yes, you should definitely keep it overlapping, because there are many flags, so there is a high probability that some will be overlapping, and the model will need to count those as 2 flags. So yes, in this case, your model should learn how to identify the overlapping flags. But in my case, in the competition where the model will run, there are just 3 flags that are scattered around the desert randomly, and the model will need to find those 3 flags. So I can safely say that the probability of 2 overlapping flags in the competition is almost 0. So in order to prevent overlapping, we could do it in multiple ways, but I will just pick a simple approach. Here, when we're picking the best X and best Y, we will instead try for a total of 30 amounts to pick a random best X and best Y position, create a new box there. Then we check if it overlaps with any of the already placed boxes, and if it doesn't overlap with anything, then we are free to consider this box one of the already placed boxes, and then break out of this mini loop so we can continue in the original loop and paste our flag and such. Otherwise, else, if we didn't break out of this, then we will just continue. We won't paste our background image and just continue for the next iteration. This placed boxes is just an array that I should define here, and this boxes overlap function is just a helper function which I can define here, it takes box 1, box 2, a minimum distance of overlapping, and it returns whether they overlap or not. Now if I tried running this code, you can see that we still have the same 100 flags, but they are now scattered evenly across the map without any overlapping. You can argue that the way I did this function may not be the best thing around. There could be more mathematical, better ways to do it. But for my case, I'm not expected to see many flags in this image. Instead of having 100 flags to generate per an image, we'll just have something around 5 or even 10 like as my maximum. I probably won't need anything more than this. So yeah, the inefficiency of this method will not be an issue with 10 flags because the probability of 10 flags at this size to overlap is already insanely small.
I have a little issue with our training set is that there is no variety here. If I played this multiple times, you can see that the desert looks the exact same. Yes, sometimes there are some noise here, some runways here, some grass here or whatever, but overall it's the same exact color of the desert because of course we were flying in the same time the entire flight test duration. What if the weather was more cloudy? What if for whatever reason there were like some fog in our camera, so this was a little bit blurry? You see where I am going? We basically need some sort of augmentation to change the color domain of the image itself so that it can reflect multiple scenarios of the desert, so that my model won't break if the weather is more cloudy or more sunny or whatever. And to do so, we will just apply the augmentation directly to the final image, and this is just a helper function that I can define here. So it's just converting my image to bytes because this is what works with torch vision, and we're just applying color jitter for the brightness at 20% shift, same for contrast, saturation at 30%, hue at 5%, and we are having a Gaussian noise. This is a helper class. It's just a standard additive Gaussian noise, honestly. Just we are having some random noise and we're adding it. So if I run this code again, you can see there is color shift in the desert image itself, which is good because our model will no longer memorize a specific desert color or such. Now, how did I come up with those values? Like, why did I pick 5% here? Well, let's just try something else here, for example, at 0.3. And if I went here, you can see that 0.3 is too much for a color shift. And a nice trick is to set both the minimum and the maximum to the same value, so that it's forced to take this exact same value each time. And then start working your way gradually until you find something you are happy with. Okay, this issue here is very fatal actually. If I zoomed closely, you can see we have our 1, 2, 3, 4, 5 artificially placed flags from our code. And there is this flag that's not placed by us. It was from the flight test itself. The reason I am saying this is a fatal mistake is because if I pass this image to YOLO and he was training and his neurons are very smart that it now can detect flags, it will have a boundary box here and say, hey, this is a flag. And then there is indeed a boundary box here, so we'll give the model a positive score or like say, yes, this is correct, you need to move in this direction. Same here, same here, same here, same here. But for here, when the model says, hey, I see a flag here, we will tell him no, there is no flag here because there is no boundary box around this area. So the model will be confused like, why is this not a flag and something like this or this or this a flag? So it will specify some neurons trying to figure out why this isn't a flag, and it will just come up with very weird patterns. That's why this is very important to check your dataset before you pass it to the training algorithm. If your training algorithm isn't doing well, it's probably an issue with your training set itself. So the way to fix this is to simply label the flags that's taken from the real world as an actual flag and give it a boundary box so that it will be treated as a normal flag. But I will not do this. And the reason is all those flags are artificially generated. Yes, different flags and yes, different desert image, but this doesn't change the fact they are artificially generated. And if my model is very good at detecting artificial flags, how can I know that it actually can generalize to real world flags like this one? How can I know that it will detect this flag well in the real world scenarios? The only way to do this is to hide this flag at all costs from our model during training, so that after my model is done training, I can insert my flag here and see if the model can detect it or not. So let's just delete those images from our folder here. So delete it. And here as well, delete. Perfect, our training set is now clean and we have our synthetic dataset generator ready. We can now start YOLO training phase, and this just requires us to create a synthetic data trainer which overrides this build dataset. And actually if I open this detection trainer and search it for build dataset, you can find this is the function we're overriding, and it is expected to return a YOLO dataset or just a normal PyTorch dataset. And this is the function blueprint, takes an image pass, which we are doing nothing with it, but it just must be there for the blueprint of the function we're overriding. And mode, the default is training, but it can be also validation. For training we have 20,000 sample, and for validation we have 1,000 sample, specifying the folders for training and the other folders for validation. And we're creating our synthetic dataset we defined above. For the training training itself, it's based on YOLO 11N, and here we are passing our YAML bus, which we defined above to a bus of our YAML file. And if I open that, this is just something required by YOLO. Here we are defining our n classes, amount of classes, which is 1, just the flag, and defining some buses here, both for training and for validation. And actually, this bus here is what's being passed to our build dataset function in its image bus variable. But of course, we are doing nothing with it. But again, this is just expected format by YOLO. Otherwise, it will give an error because we're breaking its blueprints and such. And here we are defining our trainer as a synthetic data trainer. We just defined 100 epochs. Image size, we're just picking the first element of our image size array, so 640 by 640. Finally, our batch size is 16, and we are enabling plot. Congrats, you made it to the end. If you're learning something out of the video, I would really appreciate if you can like and subscribe so YouTube can start recommending this video to more people. The channel is almost monetized, so I would really appreciate any help to speed up the process. I will also be uploading more AI tutorials soon, so make sure to subscribe to not miss out anything. See you later.